Hi there, this lecture is about simple attacks. And simple in this context means that we don't need to do low-level manipulations like overwriting pointers, injecting code, and so on. We will start with these attacks to give you some idea of how these attacks work, and also as a starter before we start going into the more complicated attacks where you exploit memory errors. So in these cases, as mentioned before, we will go for local attacks. So these are attacks where you have access to the shell. And for most of these attacks, shell access is actually quite critical, because the shell allows you to, for example, change the environment of a program. So let's go for this topic now. However, first some acknowledgements. So this section of the slides is based in parts on earlier slides made by Giovanni Vigna, who is a very prominent security researcher working at UCSB, and also Lorenzo Cavallaro, who is now a full professor in England, but before used to work here as a postdoc. So, when we run a program, we want to change its behavior as an attacker. So the first question is, what does a program behavior actually depend on? First of all, it depends on the code being run, obviously. However, a normal, well-configured system should not allow attackers to supply privileged code. That is, you should not be able to write to a file that is setuid, nor should you be able to change its owner, nor should you be able to make your own file setuid, and definitely not for another user such as root. However, this is not the only thing. The data being processed is also critical for the way the program behaves. And this part is often supplied by the attacker. So let's say you're attacking a web server. Then you're sending an HTTP request. This is the data processed by the web server. And this gives the attacker some extent of control over the program. And very, very often, exploiting a program comes down to injecting the right data, or exploit. Finally, the environment in which the program runs also matters for program behavior. For example, are there proper security policies in place? Are the file permissions assigned correctly? So these days, most operating system distributions use sensible security settings by default. But it can be very tempting, if a security setting is preventing you from doing something that you want to do, to take the shortcut and to change the settings. So programs that do this, or programs that simply don't care and for their own files set permissions that make no sense, are also risky. Moreover, it's possible in some cases that an attacker can change some configuration, especially in cases where it's supplied by the environment. These are actually many of the simple attacks that we'll be discussing. So let's say we're an attacker and we're going to exploit a program. Of course, we would never do such a thing, except to learn how to better defend the system, but for now, let's just assume that we're going to actually attack a program. So, what is the first thing we do? It's to find a target. We need to find some privileged code which we are able to manipulate. Well, as I mentioned, typically we cannot supply the code, so we need to look for something where we can either manipulate the data by providing inputs, or manipulate the environment. And then we start looking for vulnerabilities. So some vulnerabilities are deployment vulnerabilities. For example, the program might be running at a privilege level that is too high given the function that it performs, or it might perform file accesses that are insecure for whatever reason. For example, if it is setuid root, it might not check whether it actually has permission to access those files. Another set of vulnerabilities are implementation vulnerabilities, which are vulnerabilities in the program itself. Well, very common is incorrect input handling. If a program is careless in handling the input, which comes from the user and therefore might come from an attacker, it could be that, for example, it creates a buffer overflow, where depending on the length of the input from the attacker, there might be an overflow in a buffer or not. So this is a typical case of an implementation vulnerability. Likewise, it is very common to have vulnerabilities in error handling, given that this is often less tested and harder to get right than most of the regular code. because this code, the error handling, is not supposed to be executed normally. And finally, another important class of vulnerabilities in the implementations are incorrect or assumptions on the order of execution. So if we assume a particular order, but the attacker is able to run things in a different order, they might be able to use that to exploit our program. And we'll come across an example shortly. So now let's talk about attacks against the environment in which the programs run. Well, first of all, let me make clear that here I'm focusing specifically on the environment strings, rather than the more general environment as in file permissions and so on. So the environment strings is a set of strings passed from program to program that you can also specify on the shell. And it's used for a number of functions, such as locating where your programs are or locating where your home directory is. It's essentially a way to pass settings to a program that can be easily changed by simply changing the way you invoke the program. So these are not stored on disk, but these are passed along as you create a process. Well, first let us think about how processes work in Unix in the first place. So, every program that you execute runs inside a process, and the process stores all the execution state for one instance of the program. So there could be multiple processes running at the same time for the same program. They execute the same code, but they have their own independent state. Now, what do we do to run a program on Unix? First, we create a clone of the current process using the fork system call. As you can see on the right, we have program A in brown, which executes up to the point where it forks. And then it continues executing, but now twice. So the fork function is actually the only function that returns twice. It returns in each process that has been created separately. Now, in this case, one of them, typically the parent, continues running program A, whereas the second, typically the child, starts running another process. So it uses the execv system call to open the file B and execute it inside this new process. So B at that point replaces A. Now we have two processes, one running A and the other running B. So we now have seen the proper way to start processes in Unix. However, programmers tend to be lazy. And if there's a simpler way to do it, they will find it. Well, Unix, fortunately, provides some easier ways to create a process, which basically handle most of the overhead in the back, like handling how to call the right program, for example. Now, some of these alternatives are listed on this slide. For example, the function system simply takes a string and then parses this string using the shell to run it as a command. So there you specify the name of the program as the first space delimited entry in the string, whereas the parameters are specified afterwards, separated by spaces. This is very convenient, because now we don't need to split up the program and its arguments, and also the shell will look for the right program for us. Very convenient again. So no more need for separate fork and exec. popen does essentially the same thing, but also creates a pipe. So in Unix we have redirection, which is a very powerful primitive allowing us to link programs to each other using their standard input and standard output. So popen creates a pipe and links it to the standard files to allow you to communicate with the new process. Again, very convenient. And finally, we have a variant of execv, which has a p at the end, which helps you by looking up the program location. So let's say we want to run vim, then on the shell we would normally just type vim, and then the shell will look up where the program is. So execvp and execlp will do exactly this thing for us. They look up where to find vim so that we don't need to specify exactly that this program is, for example, in /user/bin. Again, very helpful for lazy programmers. So why am I discussing this? Well, it turns out that these simpler calls actually rely on the environment to do their jobs. For example, to look up where VIM is, the environment variable path is used. So the path specifies all the locations where I expect to find my programs, and if I specify a program without giving its location, then the operating system, in this case through, for example, execvp, will look for the program using the path. So it goes by the directories, separated by columns, one by one. For each checks whether VIM is there, and for the first one it finds, it picks this one and executes it. Well, it turns out, if we start a program, we can specify the value of the path environment variable. So, let's say we start a setuid program, and it uses one of these calls that look up the location of the program in the path. Now, if we do this, the attacker can modify the path and specify where to look for the program. So we can run another program, including our own. Well, this is obviously a large security risk. So this is one reason to avoid these calls in sensitive programs. There's also another one. The home directory is also stored in an environment variable, named appropriately home. So the shell actually uses this automatically to expand the tilde when you use it in the shell. So this is replaced by the value of the home variable. Again, this is something that we can change. And if we rely on the tilde being the actual home directory of the current user, then in a setuid program we could get into trouble, because an attacker can change it without changing their actual home directory. Finally, in the past there was another very strong attack using the IFS variable. And this variable changes how the shell parses commands by changing the separator. Fortunately, this hole has been plugged, and these days with setuid the IFS variable is simply ignored. So what is the lesson learned here? Well, you should really question any assumptions you may make on environment variables. Make sure that when you use one of these simple functions, you understand the consequences if they use these environment variables, because these may be under attacker control if you are setuid. So here we have a nice example program. Let's see what it does. So when it starts, it allocates a buffer of 1024 characters. And then it prints a string to the buffer. So this string will be formatted using this argument. That is, the %s will be replaced by the attacker controlled first argument. Okay? So the result is written to command. Fortunately, in this case, an attack is prevented because we're using the snprintf function. So snprintf, unlike string copy, which we saw before, actually verifies that the string fits in the buffer. So we specify the size correctly, which means that in this case we have no buffer overflow, which is of course very nice. Next, we terminate the string. No buffer overflow. Great. And then we specify the string to the function system, which happens for the return on the line of the return statement. So, is there a vulnerability here? Yes, of course there is. Where is it? Again, as before, feel free to pause playback if you need a moment to think about it. So, how can we exploit the vulnerability? Well, the vulnerability is that in this case the system function will look up where the program cat actually is. So it uses the path environment variable to search for cat. Right? Well, if we as an attacker create our own cat binary and place it in the path by manipulating the path environment variable, we can get this program to run our own program. So if this program is setuid root, we are able to break it. We are able to obtain its privileges when it's running our cat program. So this is an example how you would exploit it. So the first line, we create a program called cat in the current directory. Right? We create a script and we send these contents. So the regular marker for a shell script, the hashbang with the name of the shell, and then we simply execute the shell. Which means if we run this inside a setuid root program, it starts our cat script, and this cat script will have root privileges. The cat script starts the shell, so we get a root shell, which is basically everything an attacker could wish for. How do we achieve this? First, we make the script executable, and then we set the path. So in this case, we export path is dot, which means the current directory. So now when the program looks for cat, when calling system, it only looks in the current directory, where we just created our script. Well, now let's execute the program. The argument doesn't matter in this case. And now, rather than starting the program cat, it starts our own script. And now, assuming that the program was indeed running as root, we get a root shell. So the attack is successful. So, we fixed the program. Here there's a program that's much safer than before. How did we fix it? Well, we no longer depend on the path variable, because now we specify an absolute path. So even the system function is not going to go around looking for a program named cat. It's going to just take the absolute path that we supply. So now we are secure, right? No, of course, I would not show this slide if we were secure at this point. There's another vulnerability. So let's take a look and see if you can find it. Well, the vulnerability is here. The attacker can actually break out the /var/log directory. So the intention was for the cat program to print a log. However, the string that we specify here can not only contain file names, but also slashes and dots. Well, if we're in a directory, we can use ... to go to its parent directory. This means that we can break out of /var/log and print other files, which is obviously not the intention here. So, what can we do? Well, in this case we run example with this argument, ... /etc/shadow. So, we were in two levels of directories, so ... goes back all the way to the root. And from there, we can access any file. So now we make the program print our shadow file, which includes all the users and a hashed version of their passwords. So this attack is known as path traversal. And it's very commonly possible, not just for local attacks, but this is also a very common attack on the web. And it definitely was traditionally one of the more common attacks on the web. So again, we fixed our program. We now inserted a check. And the check makes sure that the name doesn't start with a dot or a slash. So hopefully we can no longer break out of /var/log. Well, even if this fix were correct, even then this is not good enough, because there's other stuff that we can still do. So take a look. What can we still do to attack this program? Again, we're going to rely on the fact that this uses system. System does parameter parsing. So any space that we insert will start a new parameter. Moreover, other characters like a semicolon or a pipe will start a new command. So we have an issue here. We can still insert other text, and the other text could be an additional argument for the cat program or an additional program that we're going to run. So this is an example of command injection. Let's say that we want to print syslog and then execute a root shell. Well, that is what we're doing here. So we now have an argument including a semicolon. Of course, we must use the quotes to escape the semicolon, because otherwise this would end the command on our current shell. So the quotes make sure that this is specified to example as a single argument. This single argument is passed to system, and system then parses this using the shell and finds that there are actually two commands. The first command prints /var/log/syslog, whereas the second command is the shell. So in the end, we get a root shell after printing the syslog. Additionally, there's another attack we can do here. We just had command injection, but we can also do argument injection. So cat concatenates one or more files, printing all of them together. So even if we cannot break out /var/log, even then we can specify additional arguments as well, simply by inserting spaces. Again, do note that we need to escape the spaces, because otherwise our current shell will parse them. So we simply specify the name of another file that we might want to print, and again, as an attacker, we get what we want. So by the way, do note that the argument doesn't have to be an additional path. Many commands have interesting options that allow you to read files, to change files, or perhaps even to execute files, perhaps indirectly. So the argument that you add in argument injection doesn't have to be an additional file. It might just as well be an option with a special meaning. And this, again, could be used by the programmer to subvert a setuid program. So we saw a number of cases where carelessness with user input resulted in the potential attack. So the issue here was that the user arguments ended up in the string being passed to the system function. And the system function does interpretation. So some characters can have special meaning in there. For example, the space, as we've seen, or also the semicolon, or the pipe, or any other character that starts a new command. So we have to be very careful to make sure that these characters are not interpreted by system. So one way to do this is sanitization. So by sanitizing, we either have a whitelist or a blacklist, and if we have a blacklist, we forbid all the special characters on the list, whereas if we have a whitelist, we only allow characters known to be safe. Now a whitelist is of course more secure, but might result in more users finding that perhaps their legitimate input is refused. Because if we sanitize, we fail on unexpected input, or we might simply remove the offending characters. So the other alternative is to escape, which means that we're using shell escaping, so for example quotes and the backslash, to make sure that these special characters are not interpreted as special, but are taken literally. This is generally the best solution because it still allows users to perform any operation they would otherwise be able to do. So for example, you could specify a file name with a space in it. However, you need to do it carefully, because if you don't get it right, there is still a security hole. Now I'll be discussing some attacks relating to the file systems. So file systems have a number of features that are quite relevant for security. And one example that we'll discuss here, because it's known for a particular famous attack, are symbolic links. So symbolic links allow you to create a link where one file, which is the link, points to another file. So the link simply stores the name of the other file, which is the target. And whenever a program tries to open the link, instead the operating system opens the target. Right? So this means that we can put a file somewhere that refers to another file. The syntax for this is ln-s target path link path. Right? So it looks similar to a copy command, where we copy the target to the link. However, whenever the target changes, the link also changes, and vice versa. So the program might now open the file without checking whether it's a symbolic link or not. So then it accesses the target instead. Now, what could be an issue here if the program was setuid? So the program might have verified that this file is in a particular location where the end user is allowed to write. So assuming, for example, this was a temporary file that's in a temp directory. However, if the target points somewhere else, then even though the program checked, it will not realize that it now has the permissions to write in the location the link points to, but the user does not. So it's possible for the program to modify or to read a file that wasn't intended to be written or to be read. by the setuid binary, simply because it's now in another place, where in principle, if it were a local file there, it would be allowed to do these things. So programs must be careful if they have elevated privilege to check whether a file is a symbolic link, and if so, verify that they're allowed to access the target rather than the link itself. So, if you have a setuid program, or in general, any program that has higher privilege than the user using that program to do something, you must always make sure that their privilege is not abused by the user to reveal or modify files that the user has no rights to. So this attack, where a user asks a privileged program to do more than the user is supposed to be allowed to do, is called a confused deputy problem. So basically the privileged program is acting on behalf of the user, so it's the deputy, but it's confused about what it's supposed to do and what it's not supposed to do. It's not checking whether the end user is the one allowed to do it, whereas the operating system only checks whether the deputy is allowed to do it. So, in this particular case, the attacker could, for example, make symlinks at a user-controlled path at the location of a predictable temporary file or at the location of a log file. In all these cases, the deputy might access the file thinking that it's a legitimate location for it to access. But the location it points is allowed to be accessed for the deputy, but is not allowed to be accessed for the user. As such, the deputy must check that it's not dealing with symlinks. Now, what is the solution? So there's a very nice call called access. And this system call allows you to verify whether a file can be accessed by the real user ID. So instead of checking the effective user ID, you check the real user ID. And this means that you know whether the file is allowed to access by the user rather than just by the deputy. So this should be completely safe, right? No, actually not. You shouldn't use the function access because it's inherently unsafe, it turns out. So before discussing why access is unsafe, let's first consider a nice example of a confused deputy attack using symbolic links. So this is the xterm attack, and this was a real attack. So xterm was a setuid program which was setting the ID to root, and this was necessary to allow the terminal owner to change and to access the utemp and wtemp directory, which keep track of logins. So you could log into your system with xterm and it would correctly handle everything for you. Also, xterm was able to log commands to a file, and if the stat fails on the file, there was no check. So it was basically just assuming that the file did not exist. Well, this could be abused. So let's consider these commands. First, we create a directory dummy, and then we create a link within the file directory dummy pointing to the passwd file in /etc. Now, the xterm program is root, so it's allowed to read the password file, but the user is unprivileged and is not supposed to be able to read the password file. However, this link points there. Well, if the end user uses the link, then that will be fine. The operating system will refuse access. But when the xterm program is acting on the user's behalf as a deputy, the operating system will use its effective privileges. So in that case, it will be able to access the file through the link. Now what we do is we change the permissions on the directory to not allow access inside. And then also we create a shell of our own. So also a link to the regular shell. Now what do? We say xterm-l, which means enable logging, -lf, which specifies the log file. Now the log file is dummy/passwd. Now, then we specify a command, right? So the command is echo, and then there's a string which you might recognize as a typical line for the password file. So we're adding a user here to the password file, saying that it's a log file. Now why does this work? Well, this works because the xterm program only verifies with stat, and if stat fails, it will allow the file to be used as the log file. Now in this case, stat fails because we changed the permission on the directory. However, being root, xterm is still allowed to write to the link. So even though stat has failed, now you can still write to the passwd file and add the line here. Now this line creates an alternative root user. So afterwards, we can use rlogin to log in as root, and we have completely broken access control to the system. So I mentioned access was insecure. Now why is access considered insecure? Now first let's consider how it's used. We have a simple 3-line piece of code here that performs an access check. So access path, ROK means that we verify if the real user, so not the effective user, but the user on whose behalf we're running, is allowed to read the file. Likewise, we can do a check for writing or for executing with WOK or XOK. So if we are allowed, then we will get a success return code, which is 0. And in that case, we print the file. If the real user ID is not allowed to read the file, then the check will fail. It will say that we're not allowed to read the file, and we will not try to print the file. So line 2 is only reached if the real user ID can read this particular path. Now, at first sight, this looks completely safe. But we also must consider that other things may be happening on the system while we do this. So what if the symlink changes between lines 1 and 2? So the permission at the time of use, which is line 2, so here we use the fact that we know that we're allowed to use the file, differs from the time of check, which is line 1. So if something happens in between, then the permissions may have changed, but we will not be aware. This is known as a time of check to time of use attack. And this is a common attack if you're careless with your access checks. And the issue with the function access is that it always introduces a time of check to time of use opportunity, because there's no link to the file. We just use the path again afterwards, and if the path now points to something completely different, we will never know. Now this seems super unlikely, right? However, in this case, we can see that the attacker can try again and again. So even though it seems unlikely that we happen to be able to schedule the attacker at the right time, we will just continue attempting. And the operating system scheduler regularly interrupts programs to switch to another program, to give everyone the time to run. So if it does this at exactly the right time, then the attacker will be able to violate the protection provided by access. Of course, if we run on multiple cores, it's even easier. We can just change it all the time, right? And some of the times it may happen to be the right one. So this is very likely. We call this a race condition, because essentially there is a race between the program and the attacker. Who gets to do it first? Does the program first get to print the file, so using its privilege correctly, or does the attacker get to change the link to the file first? In which case the printing will be incorrect, because it will print a file that the deputy was not supposed to print for this particular user. So what are the solutions? Well, as I mentioned, fundamentally the issue here is that we have this path, and it's looked up twice. So the first time it looks up the path for access, and the second time it looks it up for printing. So we need to make sure that the check cannot be invalidated before it's used. So what could we do? We could first open the file and then use the file handle. So when we open the file, then the file handle gets tied to the inode of the file. That is a disk data structure that is specifically tied to this file, regardless of its path. So even if the file appears in multiple paths, it will have the same inode, and any open file will be tied to this inode. If we move the file, it will still be tied to the inode, because the inode is independent of the path. And moreover, if we change the symlink, it also makes no difference, because we originally looked up the inode through the symlink, but we're no longer going through the symlink when we use the open file. Well, this works for particular cases where the suitable system calls are available to work on open files. If this is not the case, or if opening the file is in itself already an issue, for example, if we create the file if it doesn't exist, we need to be more careful. Well, there's also a general solution, and this is simply to drop privilege whenever possible. And this is generally desirable. You don't really want to have more privilege than you need. So, this brings us to the principle of least privilege. This is a general programming principle that we should follow when writing code, especially the code that has elevated privileges. So it was phrased long ago, almost 50 years ago now, as every program and every privileged user of the system should operate using the least amount of privilege necessary to complete the job. Well, this means that if we are able to write a component that has less privilege than the root, but is still capable of doing its job, we must change the privilege. We must drop the additional privileges that we do not need. So first of all, this makes it harder for an attacker to use the program for something after they get in. So let's say they abuse a vulnerability and gain the permissions of the program. They now have fewer permissions. But it also breaks attacks like these, like confused deputies, because the deputy is now no longer able to do the things it's not supposed to do. So ideally, this principle is used when designing operating systems. For example, the Multics system, which was a predecessor of Unix. Unfortunately, later this idea has been more or less dropped. And a system like the Linux kernel doesn't really follow the principle of least privilege. Instead, the entire kernel is able to do everything. So here at the View, we designed the Minix 3 operating system, which actually follows the principle of least privilege throughout, by making sure that as many parts as possible operate in user space. But this not only makes it harder for attackers to do damage, because the things they are talking to are no longer in the kernel, but rather in user space, so they are less privileged, but it also makes the system more reliable. Because even if there is a random failure, say random memory corruption, it won't be able to do as much damage if you follow the principle of least privilege. So, this very old principle remains very important for all levels of software for security and reliability, even today. So this is also known as the principle of least authority. So any component of the system where we can drop some privilege, reduce the level of authority, we should always do that. If we follow this design principle, it's much less likely that we'll be surprised with attacks like these.